Hello, my name is Lloyd Watts. I'm the CEO and founder of Neocortix. I'm very pleased to be able to present to the ARM DevSummit about our big project that we did with Folding at Home, Rosetta, and ARM to do distributed computing on ARM mobile devices to do COVID-19 vaccine research. So this is an overview of the talk. We've done distributed computing COVID-19 vaccine research on ARM devices. Let's see. So I'd like to give a brief introduction to distributed protein folding projects, Rosetta at Home and Folding at Home. These are the two core distributed computing projects that we've enabled with our Neocortex Cloud Services technology to run on potentially billions of mobile devices. And of course, those are ARM devices in vast majority. So I'll give you a brief outline on those two projects, and then the bulk of the talk will be on building the Rosetta at Home project for ARM, and then building the Folding at Home project for ARM, and then deploying at scale onto ARM mobile devices, Raspberry Pi, and ARM-based servers, and then how you can participate in this project. So first, an introduction to these two large distributed protein folding projects. First one's Rosetta at Home, and the second one is Folding at Home. So both of these projects are volunteer distributed computing projects, which in the last 7 months have been enabled to do COVID-19 simulations, focusing specifically on the spike ACE2 receptor. There's a difference between these two projects. Rosetta at Home is largely focused on static molecular simulations of how proteins fold and the configurations that they take in a sort of a static position. Little diagram there showing some of the folding positions, protein folding positions for the coronavirus spike protein. The first diagram is the spike protein without a binding molecule to it. And then the second little diagram there is the same spike protein, but shown with the a drug molecule that's being bound to it. So that's static configurations for protein folding relevant to the spike process, spike molecule in the coronavirus atom or molecule. The Folding at Home project is more concerned with molecular dynamics, and so that is how do the molecules move over time, and that enables particular analysis of the drug discovery, because these molecules can create different receptor sites which can open and close over time. And when they open up, they can expose a certain receptor site which can accept a drug or a molecule that can block that particular receptor. So the molecular dynamics is important for vaccine research so that it can determine which drugs and which molecules will effectively block the spike protein from invading human cells. Okay, so that's the two main projects that we've been focused on providing ARM support for and enabling to run on our network of mobile devices. Both of these projects have historically only been offered on Intel processors. Both of the projects are well established and have been running for many years, and their development teams have been focused historically on offering their software only on Intel processors. So when we looked at this opportunity in February and March, we realized that we could bring our network of mobile devices to help on this tremendously important health problem try to make a difference in the world. But in order to do that, we would have to have access to an ARM build of these two large programs. So now we come to why this could be of interest to the ARM dev community, the developer community, because these two projects for us now turned into a build them for ARM project. So now it's a strict developer project to build these two large software projects for the ARM platform. If we do that, we reasoned in March and February, we could allow billions of ARM mobile devices, as well as Raspberry Pi and ARM-based servers, to volunteer to fight COVID-19. So that's the setup for the project. Now, because the audience here is the developer community, the organizers of the meeting asked me to provide some technical insights into what we had to do to be able to support these two projects with ARM builds. So this core work for building for ARM was done by our lead engineer, Dmitry Moskalchuk. And so he's graciously provided me with 6 examples of techniques that he used to complete these builds. So I hope these will be of interest to the ARM developer community. They may be sort of standard techniques that would be used on any such project, but we wanted to show you the sort of highlights, examples of things that Dmitry had to do in order to be able to get these two large established projects running on ARM. So just a brief note on the scope and scale of the two different projects. So Rosetta was the one that we approached first. We were pleased to get an introduction to Rosetta by Rex St. John at ARM, who helped facilitate the relationships with the two different projects. David Kim was the lead person at Rosetta at Home and was willing to work with us. It meant that we had to negotiate with them to be able to get access to their code so that we could do that build. Dmitry took the approach of doing a cross build for ARM, that is, doing the compiling and development work on Intel machines, but doing them with an ARM target. So that was the approach that we took internally at Neocortix. There was another group of several different people associated with the project. Sahaj Sarup, David Tischler, and Ed Vilmeti are members of the ARM development community, and they were interested in doing a native build. That is where the build and compiling and development work is being done on ARM servers. So then it's a native building for ARM devices. So both approaches are valid: cross build from Intel for ARM, or native build for directly on ARM servers for ARM targets. So Dmitry took the approach of cross build, and so now that project took about 2.5 days for Dmitry to do the cross build, and then Sahaj and David followed on with the native build a few days later, and about 9 days after that, David Kim and his associates at Rosetta at Home completed their integration, and so it was only a total of about 2 weeks, and we had Rosetta up and running, publicly available for all these different communities: Neocortex, Raspberry Pi, ARM servers, to be able to access it. So that project was over and done really quite quickly in about 2 weeks. One of the reasons that it was so quick was because the scope of the project was limited just directly to take this existing code and port it to ARM, or build it for ARM. But we weren't being asked to modify the code, add any new features, anything like that. So it was a very strict porting process, which took Dmitry about 2.5 days to do. By contrast, the Folding at Home project was a much larger scope of project. It involved the Folding at Home core, Folding at Home client, and the GROMACS core and they actually asked us to upgrade the GROMACS core from GROMACS 5 to GROMACS 2020. So we weren't just building existing code, we were actually changing the code according to their specifications. And so that was not a 2-day project for Dimitri. That was more like a 2.5 or 3 month project, because we were really doing development work and upgrade work with an extended set of teams. So these projects can be small, done in a matter of days, or they can take months if they're really extended in a certain way like that. So the first one was Rosetta. The first technique that Dimitri offered to me as something that might be of interest to the developer community was simply the principle of using Docker for reproducible builds. Now that may well be known to many of the developers in the community, but it turns out that that technique had not been used internally at the Rosetta project. And so when the time came for Dimitri to provide the solution to ARM that he had done, they were thrilled when it was all packaged up as a Docker container, which eliminated all the effort that David Kim would have had to do to set up the same matching environment with all the dependencies built into it. Also, Dimitri included the dependency on a specific BOINC version, which was necessary in order to be able to make it build. That also saved effort on the part of the receiving team. So this was extremely valuable to David at the Rosetta home team. They hadn't seen this technique before, and they incorporated it into their workflow. So general technique, but it made a big difference to the receiving team. Okay, so that's the first technique. That's a high-level management technique. Now we have a more detailed problem that needed to be solved. So it's typical, when you take the existing code base and you begin your cross build, and of course it fails in a number of different ways, and you have to go hunt them down. And then once you hunt all those down and fix them, all the build problems, then you find in runtime it's failing for a bunch of new reasons, and you have to hunt all these things down. And that's why it took 2.5 days in a best case for a large project like that. So Dimitri had to hunt down and fix a number of problems. And so one of them was this particular example that he's given here was the use of, it was necessary to use correct null pointers. So when he did the build, one of the things he discovered was that one of the dependency libraries, libxml2, wasn't building properly for ARM. So he had to go find out what was the reason for it not building and find the fix. So the root cause of the problem was that library had code in it that had an Intel-specific assumption about a pointer to an empty list having a value of null. So not unusual to have the line if you're checking if the list is empty to compare the pointer value to null. That's the coding convention that was used there. It turns out that was an Intel specific assumption, and in order to make it work on ARM, he had to use the code. Basically had to use a correct ARM specific value for the pointer to the empty list. So the code snippet is shown there in the right side panel. It basically says if you're going to, it just creates a null list and then uses a pointer to that as the comparison value, rather than assuming that value is null. And it turns out in ARM, it's not null. You actually have to create that dummy empty pointer and compare it, compare your candidate value to that value in order to get a valid, correct comparison. And so that was the technique that he used for that. And of course, he had to replace all the comparisons in the code with the comparison to this newly defined null value. Okay, so that was one of the problems that had to be found and solved in the in the Rosetta project. Now we'll come to the some examples that Dimitri gave for the Folding at Home project. So the next one was, well, it's another one of these Intel-specific assumptions that if people are developing only for Intel, they may not know that they're making that assumption. But as soon as you try to do a cross-platform target, then you find out that it's specific to Intel and doesn't work for ARM. So the particular assumption here was based on the fact that char is signed on the Intel platform, but it's unsigned on the ARM platform. That's a perhaps not so well-known thing. If people are used to building on Intel, they just assume that it's signed. But we find out the hard way if we try to build for ARM that it's not on that platform. So Folding at Home built their code assuming the Intel convention, and this caused a large number of low-level crashes when we were building for ARM. So the solution was simply to make the char type signed for ARM as well. We have an example snippet of code here that shows actually the way it failed. So if you look at the top 5 or 6 lines here, that's the code that was failing. And the reason that it was failing was because it was setting this char x value in a certain condition in the if statement, the implicit if statement there, to a value of -2. That was effectively a flag value to indicate something went wrong. Setting it to -2 is obviously assuming a signed value, which is what was being assumed for the Intel code. So that's setting up the problem right there. Assigning it to -2 assumes a signed value of char, and then testing for it to be -2. Well, that fails on the ARM platform because you can try to assign it to -2, but because it's unsigned on the ARM platform, it gets a value of 254. So that doesn't work. And so the solution that Dimitri applied there was simply adding a compiler option, -fsign char, which enforces the Intel assumption over onto the ARM platform. So that fixes the problem. But it could have been a little mysterious if all you saw was the fail and didn't know what the principle was behind what the problem was. Okay, so that's the correct char type convention assumption. Okay, the next solution from Dimitri was it was necessary to use correct CPU assumptions. So inside the code, there are a number of Intel-specific assumptions for the CPU ID and Intel-specific features like SSE2 and AVX. And because those Intel assumptions were being made about what kind of processor we were running on, then the code wouldn't build for ARM, where the assumptions about the platform capabilities, so the CPU capabilities, are completely different. So Dimitri had to do some more significant work there to actually simulate the ARM CPU features, but in a way to make them appear as though they were like the Intel CPU features as much as possible. So that was essentially a little bit of reverse engineering to make these queried values come back looking like they were compatible to the Intel processors that were being expected. So there's an example here that LCF defined. If you're on the ARM platform, then he had to set this particular register, MIDR_EL1, and under certain cases, return various values. So this in place of the code and a number of other places in the code that were very similar to this were the way of essentially faking up the Intel response, the expected Intel response to these CPU queries, so that it would work even when the processor was an ARM processor. Okay, so that's that technique. And I believe the last one that Dimitri offered it was a crash problem that was occurring as a result of an incorrect minimal value of a version number of exported symbols for libc and libm. So the folding at home core was working on Intel but crashing on ARM. So the reason for this is that the libc is a very old part of the code, and it's an old component in the code. And for Intel processors, historically they were being used for a long time. So libc appeared in the fossil record of the component availability of these libraries at a very early version number. Right? ARM development came around later, and so the minimum version number for ARM was a much later version. So on Intel, glibc minimal version was version 2.2.5, a very old version, and on ARM, glibc underscore 2.17 is the expected version. So that's a much later version, version 17 versus version 2. And so if you don't instruct the compiler correctly to look for the right version, then it will crash. So straightforward fix, but you have to know what to fix and what to look for. Okay, so I believe, okay, so those were the 5 techniques that Dimitri offered just as sort of highlights of a significant development project, porting these 2 projects for ARM that may be of use to the ARM community. So once the projects were built, then the next step is deploying them at scale onto ARM mobile devices, Raspberry Pis, and servers. So Neocortex has its own platform of devices, a roster of devices that we can use to deploy. So we've deployed Rosetta at home and folding at home at a moderate scale of about 600 mobile devices onto our captive network of we have about 3,000 devices that we are currently paying for. So those devices are available to us at all times. And so for development purposes, we've been able to deploy both Rosetta at home and folding at home onto those devices and do testing at this moderate scale. Several hundred. It's a nice, sensible initial scale for testing, but it's not the billions of devices that we could potentially access. So I'll tell you in a couple of slides about the way that we are working to be able to get access to a much larger number, potentially billions of devices. But that will not be using paid devices that we're paying for. It will be devices where the owners of the devices are volunteering their services in a very compatible way that people volunteer their devices already, their desktop devices for Rosetta at home and folding at home. So at the scale we deployed, we were able to complete significant numbers of work units, and I'm showing in the right side of the display there some certificates of computation for both Rosetta at home and folding at home. So that was our small scale deployment in the initial phases of this project. But we weren't the only ones that were doing deployment. The extended ARM community, Sahaj Sarup at Linaro, David Tischler at Mininodes and Balina, and Ed Vielmetti at Packet.com, each had their own different approaches to deploying. So Sahaj and David, I believe, were focusing largely on Raspberry Pi devices, but not exclusively, also on other devices that they had in their labs. And Ed Vielmetti was focusing on ARM servers, since that's one of the business models of Packet.com. So collectively, they represented the extended ARM community, and they deployed onto a significantly larger number of devices than Neocortex currently has, because they were accessing volunteer devices. So they basically could put out a call to anyone who wanted to contribute And there was really no limit on how many people could volunteer their devices. And I believe that they got up into the number of 6,000 volunteer devices, largely Raspberry Pis, but some ARM-based servers. And if you're interested in seeing the deployment venue where you could, in fact, volunteer some of your own devices, that's foldforcovid.org, which was created by David, and is associated, I believe, with the company Bellina for whom he works. Okay, so that's deployment in a number of different directions. Neocortex doing mobile devices, and then Raspberry Pis and servers on these other platforms. Okay, so how you can participate. So coming soon, Neocortex is now working on an app called Pocket Science, and that's shown in screenshots of that are shown in the right side panel here. So the idea there is that this would allow anyone with a mobile phone to be able to contribute their device processor to coronavirus research. And the intention of the app is simply to allow you to decide, do I want to contribute my processor to folding at home, or do I want to contribute it to Rosetta at home? And if you, at the top level, if you choose one or the other, then you get one of these other two panels, which lets you set a number of different options about how much processor capacity you want to give to the project and so on. And of course, it also requires that you be plugged into the charger, plugged into Wi-Fi before your device is regarded to be ready and accessible to be used. And the reason for those assumptions there is so that plugged into the charger so that we don't run down your battery, by running coronavirus research when you're out in the world trying to use your cell phone. Right? So we don't want to run down your battery, so you must be connected to the charger in order to use it for this purpose. And you must be connected to Wi-Fi because we don't want you getting a surprise cell phone bill for your overrun on your data plan. So, so this Pocket Science app is still in development, but those are screenshots of what it will look like when it's being launched. We're expecting that sometime, probably in September, possibly early October. It's also possible for you to volunteer your devices now on Raspberry Pi and ARM-based servers. You can do that now for Rosetta. I don't believe that it's supported yet for folding at home, but foldforcovid.org will allow you to volunteer your device, your Raspberry Pi and ARM-based servers for Rosetta. Okay, and just to wrap up, I believe I've got 2 more minutes left. There's one more way that you can participate, not directly in the coronavirus research, but if you're intrigued by the idea of being able to run processes in a cloud services way on mobile devices, you can actually do that now. You can become an ARM distributed mobile developer using Neocortex Cloud Services. It's easy to sign up. Just go to cloud.neocortex.com and sign up for a free account with 100 free hours. The idea is it looks just like any other large cloud service provider like Amazon AWS or a Google Cloud Platform. It's intended to look just like those large services, but with the big difference that we run on mobile devices distributed throughout the world and for which we are paying the owners of those devices rather than buying large data centers and incurring all the high costs of that. So it's a shared economy business model. You can follow the easy steps that are shown in the right-hand panel, the tutorials, to set up your account, to be able to launch a single node, spin up a node in different ways using a web interface or a script interface. And then the 5 examples are typical of what a user would want to do, for example, to run a distributed batch Python job or a job running a binary executable with C or Go, perhaps running a render job, a large batch render job for an animation on the well-known rendering platform called Blender, or a batch load test. There's a number of applications that may be of interest to you. So we'd like to encourage you. You've got the power to run your large distributed applications on thousands of high-performance mobile devices. And hopefully, members of the ARM community will find a number of creative applications to be able to run on this exciting platform. Okay, that's the end of my talk. I'd like to stop there. I'll wrap it up there.